My name is Bobby Bills, and I'll be presenting on the characterization and mitigation of electromigration effects in TSV-based power delivery network-enabled 3D stacked DRAMs. This work is performed in the UCAD lab in the Department of Electrical and Computer Engineering under the supervision of Dr. Ishan Thakur. It has been shown recently that the performance of 3D stacked DRAMs is limited by the IR drop tolerance under power delivery networks. IR drop is dependent on the worst-case resistance seen in the PDN and limits the peak current that can be delivered to the PDN itself. The subarray activation operation has the highest peak current requirement for a standard DRAM operation. Each parallel activation increases the current requirement, and therefore the number of allowable parallel subarray activations is limited by the IR drop tolerance. The electromigration effect increases the resistance of true silicon vs into PDN over time. Electromigration is caused by the displacement of metal atoms in a wire due to a passage electron current. This causes void nucleation, which increases the resistance in the wire. TSVs are high-performance interconnects using 3D integrated circuits to connect different layers together and are susceptible to electromigration. The peak current and the number of parallel subarray activations must decrease over time to stay within the tolerance margin. This leads to a decrease in DRAM performance over time. In this work, we develop a new PDN structure, referred to as distributed PDN, that rearranges the layout of the power and ground TSVs compared to a conventional clustered PDN design. This is for the purpose of reducing IR drop noise in the PDN and increase the number of parallel subarray activations possible. We then adopt an electromigration model from prior work and apply this model to build our PDN designs to evaluate the increase in IR drop over time. Lastly, we perform analysis to evaluate the impact of electromigration cost decrease in the number of parallel subarray activations possible on different performance metrics. We model both PDN designs on a standard 4 gigabit hybrid memory cube design with 4 layers and 4 vaults. We also use a standard TSV-based PDN for our designs, with modifications made for our distributed PDN layout. The conventional clustered PDN model consists of 32 power and 32 ground TSVs laid out on both the top and bottom of every DRAM bank. On-layer rails carry current throughout the bank to deliver power to each subarray. The subarrays in the middle experience the highest IR drop due to being the furthest from the TSVs. This IR drop is what limits the number of parallel subarray activations possible. The main idea of the distributed PDN design is to reduce the distance current needs to travel to reach the target subarray in the bank. To do this, we rearrange the power and ground TSVs to lay them out throughout the bank instead of just at the edges. We divide the bank up into 8 sections, and then lay out 8 power TSVs along the top of each section and 8 ground TSVs along the bottom. We decrease area overhead by lining the power TSVs up with the ground TSVs from another section. This effectively decreases the maximum distance current needs to travel to activate a subarray. We develop IR drop maps using SPICE-based models to build PDN designs for the topmost hybrid memory cube bank. The topmost bank was chosen due to having the highest IR drop since current has to travel up the farthest along on TSVs. We tested both designs to subarray parallelism levels of 1, 2, 4, 8, 16, and 32. Our results show that the cluster PDN can achieve a maximum parallelism level of 4 without going over the 75 millivolt IR drop margin, while the distributed PDN can achieve 32 subarray level parallelism and still be below the margin at 64.4 millivolts. Our electromigration model is adopted from a prior work and is used to model the void radius growth over time in a PDN due to electromigration. We develop another model for the resistance gain as void radius grew. This model is also based on the same prior work and on a relationship presented there. Using the electromigration model, we first evaluate the subarray parallelism over both PDN's lifetimes using 9 parsec benchmarks. We find that for every benchmark tested, the distributed PDN achieves higher or at least the same level of subarray parallelism throughout its lifetime than the clustered PDN does. In addition, for every benchmark tested, the distributed PDN has a higher lifetime than the clustered PDN does. We evaluate the performance over time by running simulations using NVMe. On average, the distributed PDN is able to achieve lower levels of average access latency than the clustered PDN. This is due to distributed PDN being able to parallelize more subarray activations at once. The distributed PDN is also able to achieve higher levels of access throughput compared to the clustered PDN across all benchmarks tested. The distributed PDN is able to accomplish this due to a larger value for the number of parallel subarray activations possible, which allows for more read and write requests to be served in a length of time. The energy delay product, or EDP, was calculated using a formula on the right. It was then normalized relative to the clustered PDN's EDP at 0 years. As can be seen, on average the distributed PDN was able to achieve better normalized EDP over time than the clustered PDN. This is again due to higher levels for the number of parallel subarray activations possible. In conclusion, we proposed a new PDN design that rearranges the power and ground TSVs in order to reduce IR drop noise. This distributed PDN was able to achieve higher values of subarray level parallelism, had a longer lifetime, and it showed improved performance metrics over its lifetime. Therefore, it can be said that our distributed PDN offers a superior solution for mitigating the effects of electromigration-induced aging on the lifetime of 3D stacked DRAM architectures. Thank you for watching.